Hello everyone and welcome back to another video. In this video we're going to finish off section 1.1, which is all about approximating areas. So remember in the last video we had this example where we were trying to find this area A, which we said that area is equal to the integral from 1 to 2 of x squared dx. So we were trying to approximate that area, and we were doing so by using rectangles and finding the areas of the rectangles and summing them together. So remember that we said we can do a left point approximation, a right point approximation, or a midpoint approximation. In this example, I use the midpoint. As you can see, the midpoint of each rectangle is used for the height of the rectangle. That's just for convenience. So what I want to talk about now is how can we make our approximation for A more accurate, right? So basically we discussed in the last video how the midpoint approximation usually is better than the left and the right endpoint approximation, simply because there's area missing underneath the curve that cancels out with area above the curve. And so the error between the actual area A and the midpoint approximation is less than with the left endpoint and the right endpoint, right? But we still see that we're off because there's still gaps in the area and over accounted for areas as well. So we're not perfectly estimating this. How do we make it more accurate? Well, let's take a look at a few pictures. So in this picture, we have two rectangles. Graph. I don't know why I'm saying picture. So then in this graph, we have, let's see, 1, 2, 3, 4, 5 rectangles. So in this one, we have 5 rectangles. Well, when we say n, you should know that means the number of rectangles. In this picture, I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 rectangles, right? And in this picture I have 1, 2, 3, 4, 10, 11, 12, 13, 14. I have 20 rectangles, and in this one I had put in 50. So as you can see, right, as we increase the number of rectangles, the area error, right, the area that we're missing and the area that's overcounted for shrinks as we increase the number of rectangles. So that is how, right, in this one it's hard to see, but there is still error, right, where there's a little tiny area above and little tiny areas below that are missing. But once we get to 50, that's virtually known, right? This is a pretty good approximation for A. So the conclusion that we draw then is that the more rectangles we use, the better, right? So conclusion, the more rectangles used, the more accurate the approximation. And I hope that this reminds you of something that we learned about in Calculus 1, which, remember, is the limit, right? So basically what we end up with here is that the limit as n approaches infinity of any of our approximations, right? So in this case we were doing the midpoint approximation, so remember that the notation is m, capital M for midpoint approximation, and the lowercase n for the number of rectangles. So if we bring the number of rectangles off to infinity, that means we increase the number of rectangles as much as possible, then that's going to give us an approximation for A, a very close approximation for A, right? That's what we're seeing here, where this space here is essentially the same as this space here, A. So that holds for each of the rectangle approximation techniques that we learned, right? For the right endpoint, for the left endpoint, and for the midpoint.